Hey, today we are going to combine and compose functions. I think you'll like it. What I need you to do is put a title on your notes and copy the 1, 2, 3, 4, 5, and 6 functions I have here. Pause the video if necessary. So we're going to look at combinations first, and part A of combinations is to just review how to evaluate. So if I ask you to evaluate f plus g of 1, you simply say, well, that means to do f of 1 plus g of 1. So f of 1 would be 1 squared minus 1, which is 0, minus 12. And g of 1 would be 2 times 1, which is 2, plus 1, which is 3. So I'm getting negative 9 for f plus g of 1. So if I ask you to evaluate g minus q of negative 2, you're simply going to say, well, do g of negative 2 minus q of negative 2. Well, g of negative 2 is 2 times negative 2 is negative 4. Negative 4 plus 1 is negative 3. Minus, now q of negative 2, q is blue, so they'll rhyme. So blue of negative 2 is negative 2. So I would put a negative 2 here. And of course, I can see that's negative 3 plus 2. So that's negative 1. Let me adjust the camera. Now we're going to do kh of negative 5. So I need to do k of negative 5 times h of negative 5. So k of negative 5 would be the square root of negative 5 plus 9. Let's see, negative 5 plus 9 is 4, and the square root of 4 is 2. H of negative 5 would be negative 5 squared, which is 25, plus 6 times negative 5, which is negative 30. So 25 plus a negative 30 is negative 5, and that's negative 10. Last but not least, f over h of 10 is f of 10 over h of 10. So f of 10 is 100 minus 10 minus 12, so that's 100 minus 22. I think that's 78. H of 10 is 100 plus 60, so 160. And then I believe I can reduce that. 78 divided by 2 is 39, and 160 divided by 2 is 80. Now, you'll notice that in all of these, when I said we're combining means that you're adding, subtracting, multiplying, or dividing. Now, the second thing that we're going to do with combinations is to write equations. So you take two existing functions and you create a brand new function by adding or subtracting or multiplying or dividing. So h minus g of x would be to take the equation for h of x, which is x squared plus 6x, and subtract the equation for g of x, which is 2x plus 1. And we're going to create a brand new function. So x squared plus 6x, distribute the negative. Now, what I don't want you to do is just on your paper write x squared plus 4x minus 1, because this is not an equation. This is an expression. So if you want an equation, then name that h minus g of x. So now I have a new function name, and I have the rule or the equation for the function. So I'm going to be particular about, if I ask you for an equation, but you give me an expression, it won't be complete. All right? So let's look at the equation for f h of x. All right? So I need the equation for f of x. So the equation for f of x is x squared minus x minus 12 times the equation for h of x, which is x squared plus 6x. So right now it's in sort of almost factored form, not really. But what I'm going to do is I'm going to recreate the equation in standard form. So I simply have to multiply the trinomial by the binomial. So x squared times x squared is x to the fourth. X squared times 6x is 6x cubed. And then I've got to say negative x times x squared is negative x cubed. Negative x times 6x is negative 6x squared. Then negative 12 times x squared is negative 12x squared. And negative 12 times positive 6x is negative 72x. So now let me clean that up. So I'll have x to the fourth. Let's see, that gives me plus 5x cubed. This gives me negative 18x squared, and then minus 72x. Now, I don't want to go right back and factor it because then I would be going back to where I started. So I'm going to say my new equation now is FH of x is x to the fourth plus 5x cubed minus 18x squared minus 72x. Now, before I do a third one, I want to mention that when you add, subtract, or multiply two known equations, you don't change the domain. So if you'll notice, f, g, and h are all polynomial functions, and their domains are all real numbers. So the domain of any combination where I add, subtract, or multiply also creates two. In this case, both of these are polynomial functions, so the domain is also all real numbers. When you divide functions, however, you can create new domains. So let me erase what I've got so I can make room. And what I'd like you to do is give me the equation for g over f of x. Well, to create the equation, it's pretty easy. I just take the equation for g of x over the equation for f of x. So I've created, out of two polynomial functions whose domains were all real numbers, I've created a new rational function. But if I said, what's the domain of the rational function? You need to say, wait a minute, the bottom cannot be 0. So x squared minus x minus 12 cannot be 0. So if I factor that, I'm going to have x minus 4 and x plus 3 cannot be 0. So x cannot be 4 and x cannot be negative 3. So then if I said, well, what's the domain for g over f of x? You're going to say the domain is the set of all x's such that x does not equal negative 3 or 4. So remember, just saying this, that's not putting it into a proper domain notation, and you know that I'm expecting good notation. Now, if you want to get into notation, this is not the only option. You could also say it's everything up to negative 3, everything between negative 3 and 4, and everything after 4. So either of those would be good notation. Now, the third and final thing that we're going to do with combinations is to create new graphs. So notice that I'm asking you to graph P plus Q and Q minus P. And so you're going to look at your current graphs and we're going to go from there. Well, I can tell you that one way to get organized, and you might think, well, that's going to take extra time. But it turns out that I think if you go ahead and do this on the front end, you actually save time. So we're going to create a T-chart. Now, it doesn't matter if you say P plus Q or Q plus P. The way you add two things doesn't matter, but when you subtract, it does matter. So I'm going to make it a T-chart, and I'm going to put Q first when it matters. So my T-chart should go from my left most x at negative 3 to my right most x at positive 3. And I think ultimately this could be a time saver for you. So I'm going to do Q first because Q matters here. And I'm going to do P second. And then I'm going to get my combinations. Now, I know Q is blue. Tried to do that to help you. So if you'll go through and you'll look at your Q graph, I see that -3 is -1, or the point -3, -1 is on the graph. -2, -2 is on the graph. -1, -1 is on the graph. 0, 0, 1, 2, 2, 0, and 3, 3. So then on my green graph, I made the P of X graph green, since I know when we eat fresh green peas out of the garden, those colors go together. So P of -3 is 1. P of -2 is also 1. P of -1 is 3. P of 0 is 0. P of 1 is -3. P of 2 is -1. And P of 3 is -2. Okay, now I am simply going to get the values for my combinations. So if I do Q plus P of X, then I simply add my Y values. So -1 plus 1 is 0. -2 plus 1 is -1. -1 plus 3 is +2. 0 plus 0 is 0. 2 plus a -3 is -1. 0 plus a -1 is -1. And 3 plus a -2 is 1. So now I can do the graph here. So let's see here. I've got -3 to the left, +3 to the right. So I need to start out and plot -3, 0, -2, -1, -1, 2. And I'm going to start connecting along the way. 0, 0, 1, -1, 2, -1, and 3, 1. And that's my graph of Q plus P, or P plus Q. So now I'm going to figure out what the graph of Q minus P of X is. So I need to do the blue Q values minus the green P values. So right here, I've got -1 minus 1 is -2. -2 minus 1 is -3. -1 minus 3 is -4. 0 minus 0 is 0. 2 minus -3 is 2 plus 3 or 5. 0 minus a -1 is 0 plus 1, which is 1. And 3 minus a -2 is 3 plus 2 is 5. So now let me go ahead and graph this one. So I've got 1, 2, 3 to the left and to the right. Now it looks like I go as low as -3 on my Y values and as high as +5 on my Y values. So I'm going to plot -3, -2, -2, -3, -1, -4. Oh, I didn't catch the -4. 0, 0, 1, 5, 2, 1, and 3, 5. So there's nothing real difficult about it. I'm basically just getting you to add and subtract. And in this case, it would be, let's see, for 7 different X values, 7 different problems, and then plot the points. It's really pretty easy. Now we're going to look at composing functions or compositions of functions. That's when you nest one function inside another and you work your way inside out. So if I ask you to evaluate f of g of 3, evaluating, writing equations, and graphing are going to be my A, B, and C parts for compositions too. So the first thing I need to do is evaluate g of 3. Well, g of 3 would be 6 plus 1, 7. The next thing I need to do then is evaluate f of 7. So that would be 49 minus 7 minus 12. You don't have to show work. So that looks like it would be 49 minus 19. I'm thinking you get 30. Okay? So then f of g of 3 equals 30. And if I were plotting points and graphing functions, I would know 3, 30 was on the graph of f of g of x. So if I ask you to do h of k of 16, let's see here. K of 16 is going to be the square root of 16 plus 9. That's the square root of 25. That's 5. So I need to do h of 5 now. H of 5 is going to be 5 squared or 25 plus 6 times 5 or 30. So 25 plus 30, I think I can do that in my head, is 55. Okay? So Q of G of 0. So G of 0 is just 1. So I'm going to ask you to evaluate Q of 1. So I need to look at blue Q. Q of 1 is 2. Now we've got one of these crazy ones. So let's talk our way through it. So the first thing is Q of negative 3. Q is blue. So Q of negative 3 is negative 1. So I've done this and I've gotten negative 1. Now I need to do P of negative 1. Well, green is P, so P of negative 1 is positive 3. So now I've got positive 3 for that part. Now I need to do K of 3. Well, K of 3 would be the square root of 12. So I'm going to have the square root of 12, which I can break down in a minute. And then I've got to do H of the square root of 12. Well, H of the square root of 12 would be the square root of 12 squared, which is 12, plus 6 times the square root of 12. So I've done the right work. I just need to finish it. So I know that 12 is 4 times 3, so that's 2 square root 3. So my final answer is going to be 12 plus 12 square root 3. So I know that you feel comfortable with evaluating. Let's move on to writing equations. So if you see this notation, you say F circle G of X. This is not my favorite notation, but sometimes it's necessary, especially when you get into some upper level stuff in calculus. But this just simply means write the equation for F of G of X. Now I'm going to ask you to show 3 steps. So I'm going to say, show the interior function. I'm also going to say, show what it looks like to plug it in. So set it up. And then last but not least, clean it up. All right. And let me remind you that the final answer should be an equation. So when I say show the interior function is g of x, and g of x is 2x plus 1. So show 2x plus 1. Now show what it means to plug it in or set it up. So remember, f of whatever is going to be whatever squared minus whatever minus 12. So in this case, it's going to be whatever squared. I'm going to erase this. Minus whatever minus 12. So now I've set it up, and now I'm going to clean it up. So when I clean it up, I know the square of this really fast is 4x squared plus 4x plus 1. Distribute the negatives, so minus 2x minus 1, and then minus 12. So I'm getting 4x squared. 4x and minus 2x is plus 2x. The 1 and minus 1 cancel, so I think it's just minus 12. Now, to finish it up, I'm going to say F circle G of X equals 4x squared plus 2x minus 12. If you would prefer to write f of g of x equals 4x squared plus 2x minus 12, that's okay too. So now let's go in the other direction. Let's do g of f of x. So I am going to write g of f of x because I like that better. I feel more comfortable with that. So step one, show the interior function. Well, the interior function is f of x, and that is x squared minus x minus 12. Now set it up, show what it looks like to plug it in. So g of whatever I plug in is 2 times that whatever plus 1. So it's 2 times that whatever plus 1. Now clean it up. So I get 2x squared minus 2x. And then I'm going to say minus 24 plus 1's minus 23. I'm going to go ahead and get to it. Now don't forget, make the final answer an equation. So g of f of x equals 2x squared minus 2x minus 23. And remember, here's f of x, f of g of x. Here's g of f of x. They tend not to be the same answers. So don't assume it's going to be the same thing either way. Let's write the equation for k circle h of x. This one's kind of fun. Well, first off, I know this means k of h of x. Show me the interior function. What is h of x? H of x is x squared plus 6x. Now, show what it looks like to set this up. Show what it looks like to plug it in. So I remember that k of whatever is the square root of whatever plus 9. So it's the square root of whatever plus 9. So I've got that. Now, I wonder if that can be cleaned up. Well, do you recognize that x squared plus 6x plus 9 factors into x plus 3 times x plus 3, which of course is the square root of x plus 3 quantity squared, and that's equal to x plus 3. Now, I will let you get away with this in pre-calculus, but technically what you need to say, and it's going to matter in calculus, is that whenever you take the square root of something, that something must be positive. Therefore, the real answer to this is the absolute value of x plus 3. Don't forget, it's got to be an equation. So k of h of x equals the absolute value of x plus 3. One last thing, you can compose a function with itself. So you could do h of h or k of k or g of g. So if I do g of x, I'm going to do a simple one. Well, g of x is 2x plus 1. So it's just g of 2x plus 1. And what's it look like to plug 2x plus 1 into g of x? Well, it's 2 times whatever I plug in plus 1. So that becomes 4x plus 2 plus 1 is plus 3. So g of x, or you could say g circle g of x, is 4x plus 3. Now notice that I've not been mentioning much about the domains of compositions. I'm going to talk more about the domains of compositions in a little bit. That's probably the trickiest part of this lesson. Now we're going to talk about graphing compositions. And so you've got to have a graph of each of these to do this. Well, I have the graphs of p of x and q of x. And remember, to graph p circle q of x just means to graph p of q of x. Now, here's a time when for sure you don't have to do a t-chart, but what I notice is people sometimes get themselves more confused if they don't, and that slows them down. So really, doing a t-chart, it might be a little investment of time on the front end, but it tends to actually speed people up, so I'm going to do it. Well, on both p of x and q of x, the current graphs have a domain of -3 to 3. So that's how I'm going to make my t-chart. It's from -3 to 3. So I've got -3, -2, -1, 0, 1, 2, and 3. So I'm going to start out and let's do p of q of -3. And that's equal to p of, well, if you look at your graph, Blue Q of -3 is -1. And then P of -1 is green of -1, and that's 3. P of Q of -2 is P of, so do blue Q of -2. Blue Q of -2 is -2. P of -2 would be green of -2, and that's 1. So P of Q of -1 is blue Q of -1. So blue of -1 is -1. P of -1 is going to be green of -1, which is 3. P of Q of 0 is going to be P of blue of 0 is 0. And then P of 0 is green of 0. That's also 0. So P of Q of 1 is P of, now Q of 1 is blue of 1, and that's 2. And then P of 2 is green of 2, and that's -1. P of Q of 2 is P of Q of 2 is blue of 2, so that's 0. And then P of 0 is green of 0, and that's 0. Last but not least, P of Q of 3. You have to do Q of 3 first. That's blue of 3, and that's 3. And then P of 3 would be green of 3. Green of 3 is -2. So what's that mean for your graph? So now I need to draw a graph where my domain is -3 to 3, and my range is also going to go -3 to 3, or maybe a little bit less. So I'm going to plot -3, +3, because I plugged in -3 to begin with, and I got +3 on the first row. -2, 1, because I plugged in -2, and when I worked it all out, I ended up at 1. -1 and 3. 0, 0. 1, -1. 2, 0. And then 3, -2. So that's all you have to do to graph a composition. The main thing is just to take it a little slow and make sure you don't misfire on your points. It's not real difficult. Now we're switching gears. I'm going to move away from the F, G, H, K, P, and Q of X that I gave you initially. And we're going to do our last 2 topics. This one's kind of fun. This one requires creativity. Now you're used to, if I said, hey, here's an equation for U of X, and here's an equation for V of X, give me the equation for U of V of X. And we just went through how to do that. 3-step process, show the interior function, set it up, clean it up. Now I'm asking you to go in reverse. So it's a little bit higher order thinking skill, and it requires creativity. And I'm also going to ask you to do one more thing. Now the book sometimes will ask you to just give 1 pair, but I will generally ask you to give at least 2 pairs. So here is W of X. I want you to come up with a U of X and a V of X so that U of V of X equals W of X. And my only restriction is that you can't let U of X or V of X simply be X, okay? So there's usually, especially with the ones I'm coming up with, more than one way to do it. So what I tend to do is look at the inside function. So the inside function, by the way, is V of X. Well, I tend to practice every single way I could do an inside function. So if I look at this, the first thing that I notice is that the inside function could be the x squared plus 1. And then the outside function would be the cube root of that. And this is setting you up for something called the chain rule when you're in calculus. It's good to be able to see how an exterior function is acting on an interior function. And you might be going, how did you get that? Well, if I did U of V of X, I would be doing U of my interior function, and U of whatever tells me to take the cube root of whatever. So I'd take the cube root of whatever And notice this does equal the W of X I asked for. So that means I found a good combination for U of V of X. Now, it's not the only answer. Could I go smaller for my V of X? And the answer is yes. V of X could have been just X squared. Can you take a stab at what U of X would be? If you said the cube root of X plus 1, you are correct. Because you're taking U of V of X, meaning you're inserting V of X in place of the X and U of X. So if you took this X squared and put it right here, you would have the function that I prompted you with. So those are two good answers. Now, there could be more answers. I would have to get a little creative, but I don't want to do that because here, simpler and more obvious is better. Because we're trying to see how an interior function acts if it's placed inside an exterior function, and that will take us into calculus and the chain rule. So I don't want anything fancy. So you might be going, yeah, but what's fancy? Okay, so could I do something like, how about V of X equals the 6th root of X squared plus 1, and U of X would be maybe X squared. Well, I don't know. Let's see. If I did this, then U of V of X would be U of the 6th root of X squared plus 1. So if I plug that in, U of X is whatever I plug in squared. So whatever I plug in squared, well, that's going to be X plus 1, if I say to the 2/6 power, that's equal to X plus 1 to the 1/3 power, and that's equal to, I've lost my X squared, sorry about that. That's equal to the cube root of X squared plus 1. So that is what I started with for W of X, but this is reaching. And this particular scenario, be as vanilla as possible, and that's your best bet. Here is another example, and I want you to come up with more than one pair. So I want you to come up with at least 2 pairs. So does anybody have an idea for what the interior function could be? You don't have to do the interior function first, but that seems to be the easiest thing for me. So I might say the interior function is all of 3x plus 1. Well, if you did that, would you recognize that U of X would have to be 5 over X to the 4th? Again, if you put 3x plus 1 in place of that X, let me show you again. In this case, V of X is 3x plus 1. U of whatever is 5 over whatever to the 4th. So it's 5 over whatever to the 4th power, and that matches our W of X. All right, let's keep looking. What are other options for U and V? So again, I have more luck if I play around with my interior function. Could I let V of X be a little bit bigger? Could I let it be all of 3x plus 1 to the 4th? I hope you're saying, yeah, that would work, because then I could let U of X be 5 over X. So 3x plus the 1 to the 4th just pops right there, and that would give me my original fraction. Well, I've gone bigger. Could I go smaller? So I went from 3x plus 1 and I made it bigger, 3x plus 1 to the 4th. Could I go smaller? Well, I would say, yeah, you could let V of X equal 3x. Well, then U of X would be 5 over X plus 1 to the 4th. So again, if you pop this 3x right here in place of that X, that does give you the original function, okay? So this is more fun when we're all together and you all can throw out ideas, but this is the basic idea. Okay, so I'm going to issue a challenge problem. Here's your W of X, and I've made it pretty convoluted. That means there's going to be a lot of options. I challenge you, can you come up with 3 at least ways to write a u of x and v of x combination, but I think that there are actually 4 really good ones. Try it. I hope you paused the video and you tried it for yourself. So here I go. When I look at it, I think, well, actually I'm thinking there's 5 of them. The biggest v of x I could think of is if you made all of this equal the interior function. Then would you see that u of x would be all of this minus 3 or x minus 3? That's one pair. All right. So can I go a little bit smaller on my v of x than this? Well, yes. Now I'd probably say let v of x just be this part, the 2x cubed minus 5 squared. So then can you see that as v of x gets smaller, u of x is going to be a little bit bigger. So u of x would have to be 4 times all of this minus 3. So if I put all of this in place of x, I would go back to this function. Okay, so can we go a little bit smaller with v of x, which will make u of x a little bit bigger? So smaller than this. What about making it 2x cubed minus 5? So can you tell that u of x then would need to be 4x squared minus 5? So all of this goes in place of x and you square it. That's going to give you the original. So can you go even a little bit smaller for v of x, which is going to make u of x even bigger? So what about just making it 2x cubed? That's a little bit smaller than 2x cubed minus 5. Well, then u of x would be 4 times x minus 5 squared minus 3. Have you gotten any of these? I hope so. Well, I'm thinking there's one more good option. So if v of x equals smaller than 2x cubed, 1x cubed, then u of x would be 4 times 2x minus 5 squared minus 3. All right. Some of you may think, whoa, well, let v of x be 2x. But the problem is, if, let me show you. This would not be right. But this is what some people think you could do. It's just a misfire. It's a good idea. It just doesn't quite work out. They'll say, well, let v of x be 2x, and then let u of x be 4 times x cubed minus 5 squared minus 3. The problem with that is when you did u of v of x, and you plugged in, let me show you what I'm doing, then you're going to have 4, and you would have to put 2x right here. So it would be 2x cubed minus 5 squared minus 3. And that would give you 4, and then this would wind up being 8x cubed minus 5 all squared minus 3. And that is not your original double u of x. So you're almost right, just not quite. So I mentioned earlier that we weren't going to yet talk about the domain of compositions. Well, now we are. And what I want to show you is that number 1, you don't have to actually find the equation of the composition to find its domain. And number 2, finding the equation of the composition might actually confuse you about its domain. So let me show you how you do this. So find the domain of a of b of x and of b of a of x. Well, the best thing to do is to start out with the domain of each individual one. Well, I know that this is a cube root function, and I can always take cube root. So the domain of a of x is all real numbers. Well, I know that this is a rational function, and I can't have 0 on the bottom. And I can quickly tell that x can't be 3 or negative 3, because then x squared would be 9, and 9 minus 9 would be 0. So the domain on this one is all x's except for plus and minus 3. Okay? Now, my first question is, what is the domain of a of b of x, or of a circle b of x, okay? Well, if you look at it, guys, I'm not going to write the equation because I want to show that you don't need to. Well, when I start to evaluate, if I were to say evaluate a of b of this or a of b of that, do you see that you'd first evaluate b of x for some x value, but you can't evaluate b of x at 3 and negative 3. So we can't evaluate b of 3 or b of negative 3. So that's telling me x cannot be plus or minus 3 in this problem. All right, so I know not to plug in 3 and negative 3 from the get-go. But now I have to say, is there anything that I'm going to get from my b of x answers that I then can't plug into a of x? Well, a of x accepts all input values. So no, anything I get as a b of x answer could then be plugged into a of x. So the only hang-up I have is that I can't start by plugging in 3 and negative 3. So I'm going to say my domain for a of b of x actually matches my domain for b of x. So the interior function created my only, the only reason that I had to restrict my overall domain. So now let's do the domain of b of a of x. So I first have to say, well, I would evaluate a of x first. Is there any x value that I can't plug in and evaluate when I do a of x? Well, no, I can plug in anything I want to, so no restriction. So then I have to say, well, I'm going to take answers for a of x and I'm going to put them into b of x. Are there any output values for a of x that would cause me problems plugging into b of x? Well, yes, I can't plug in a of x equals 3 or a of x equals negative 3 when it's time to plug in into b of x. So, okay, a of x cannot be then 3 or negative 3. Well, a of x is the cube root of x plus 2. That cannot be plus or minus 3. So cubing both sides, x plus 2 cannot be plus or minus 27. So subtract 2 from both sides. This is telling me that x cannot be negative 2 plus 27 and negative 2 minus 27. And you might be going, what? That doesn't make sense. So think about it, guys. If I ask you to evaluate, if you don't understand this, I said, okay, so evaluate. If you don't believe me, evaluate b of a of 25. Well, if you tried to do that, you would say, well, let's see here. Evaluate a of 25 first. Well, a of 25 would be 25 plus 2 is 27. The cube root of 27 is 3. So now evaluate b of 3. But wait, I can't evaluate b of 3. B of 3 would be 1 over 9 minus 9, which is 1 over 0. B of 3 does not exist. Whoa, if b of 3 does not exist, it means 25 was what was not in the domain of b of a of x. So now I'm going to say the domain of b of a of x is all x is such that x does not equal negative 29 and 25. So again, depending on which way you're doing the composition, your domain can be radically different, sometimes easier, sometimes harder. So I'm asking the same question, but I have changed my a of x and my b of x. So this time I need to start by finding the domain of the individual functions. So I see for a of x it's rational and I can't have 0 on the bottom. So that means I can't have 0 for x. Well, b of x is also rational, and so I can't have 0 on the bottom, so I can't have x to be 6. Okay, so let's see how this works out. So first I want to look at the domain of A of B of X. All right, so let's see here. I start by evaluating B of X, and I know I'm not allowed to plug in X equals 6. So avoid X equals 6 because you can't get started with B of X that way. Okay, now the next thing I do is I get my answers for B of X and I plug them into A of X. Is there any answer for B of X that could not be plugged into A of X? Well, A of X will not allow you to plug in X equals 0. So that means whatever I get for B of X, it better not be 0 or I can't plug it into A of X. Well, that means 1 over X minus 6 better not be 0. But guys, it's not going to be 0 anyway, because the only way that a fraction can be 0 is if the top is equal to 0, and that 1 is never going to be 0. So this part becomes a non-issue. This part becomes the only thing that actually has an effect. So I'm going to say, okay, so all X such that X does not equal 6. Now, it's just a coincidence. There's no rule that says the domain of one of the compositions will always be an exact match. It's just the way that these problems worked out. So now let's do the domain of B of A of X. So if I were to evaluate B of X, I would evaluate A of X first. Well, I can't evaluate A of X if I start by plugging in 0. So I have to say, remember, don't start out with X equals 0 or you can't get anywhere. All right. So then I have to say, once I evaluate A of X, I plug those answers in as the X values for B. So are there any values that I could get for A of X that I can't plug into B of X? So I'm going to say, well, A of X better not be 6 or I can't plug it in to B of X. Hey, so what I'm going to do is I'm going to solve this equation by cross multiplying. So 6x squared better not be 1. X squared better not be 1/6. Running off the screen a little bit. That means X better not be plus or minus the square root of 1/6. X better not be the square root of 6 over 6, plus or minus. So again, on this one, now I've got 3 things I need to say. The domain of the composition excludes 0 and plus or minus the square root of 6 over 6. Now again, if this is like kind of bothering you, if I ask you to evaluate, let's evaluate B of A of 0, okay? Well, you would say, well, that's B of, let's see, A of 0. I can't do A of 0. That's my point. You can't do A of 0, so you can't do B of A of 0, so 0 is not the domain. Okay, now let's try B of A of the square root of 6 over 6. All right, let's try that. Well, I start out by doing A of the square root of 6 over 6. Well, A of the square root of 6 over 6 is 1 over the square root of 6 over 6 squared. So that would be the square root of 6 squared over 6 squared. Well, that is 1 over 1/6, and 1 over anything means reciprocal. So 1 over 1/6 means 6 over 1. So I should say it's B of all of that, because I'm just working on the A part. So now let's evaluate B of 6. But I can't evaluate B of 6 because it would give me a 0 in the denominator. So if I can't evaluate B of 6, it's because I wasn't supposed to plug in the square root of 6 over 6 from the get-go. All right, the last one we're going to do is to find, again, the composition domains. So here, I know that, wait a minute, A of X is a square root function, so its domain is restricted. And I know that I have to take the square root of 0 or the square root of positive numbers. So what's under the radical cannot be negative. It must be positive or 0. So x must be greater than or equal to 1. So the domain is 1 to infinity, or x such that x is greater than or equal to 1. For b of x, it's a polynomial function. It's quadratic. And the domains of all polynomial functions are all real numbers. So that's fine. That's not my issue. So then let's do the domain of a of b of x. Okay, so I would evaluate b of x first. B of x accepts any input value, so I have no restrictions there. I need to make sure that my answers for b of x that are going to be plugged into a of x are allowed. So my answers for b of x have to be in this domain. So I'm saying that b of x must be greater than or equal to 1. All right. Well, b of x is x squared plus 5, and that must be greater than or equal to 1. Wait a minute, that means x squared plus 4 must be greater than or equal to 0. I'm solving a polynomial inequality. But guys, don't think too much about this. Remember, if x is 0, 0 squared plus 4 is greater than 0. If x is anything negative, negative squared is positive, plus 4 is positive, and positive is greater than 0. And if x is any positive number, a positive number squared is positive, plus 4 is a positive number, and that's greater than 0. So guys, this is always true. That means this does not present a problem. Therefore, I had no problems plugging into b of x, and nothing that I get out of b of x is a problem when I plug it into a of x. So that was kind of a surprise. The domain of a of b of x is all real numbers. Now, let's look at the domain of b of a of x. Okay? Well, the domain of a of x, that's where I start plugging in. Well, I can only plug numbers into a of x that are larger than 1. So I'm going to remind myself x has got to be greater than or equal to 1 just to get going. Well, the domain of b of x is all real numbers. So anything that I get as an answer for a of x, I can plug in. I can plug into b of x. So the only issue I have is I've got to start out with x is greater than or equal to 1. So I'm going to say this domain is also 1 to infinity. Okay? Now, let me show you the problem. If you had actually worked the equation, you would have had that b of a of x is b of the interior function. And you would have said, okay, b of whatever is whatever squared plus 5. So whatever squared plus 5. Well, that would be x minus 1 plus 5. And that would be x plus 4. So you would have had the equation for b of a of x is x plus 4. And you would have said, Miss Porter, this is a linear function that looks like this, and the domain's all real numbers. But the domain is not all real numbers. It's 1 to infinity. And you would have confused yourself if you had actually found the equation of the composition. And you still might be going, that's not true. The domain of this line is all real numbers. And so I'm going to back up and I'm going to say, fine. If the domain of this composition is all real numbers, you ought to be able to evaluate anything. So here I go. I am going to ask you, please evaluate b of a of 0. All right. Well, you have to evaluate a of 0. That would be the square root of negative 1. But that's I can't have imaginary y values. So that actually means that a of 0 does not exist. So that means that 0 must not have been in the domain. I can't get b of a of 0 because I wind up getting in all this imaginary stuff. So that's an example of finding the equation can actually lead you astray in the domain. So actually, if you want to be straight up about it, Remember when I did the equation for B of A of X? And I think I got X plus 4 if I remember correctly. Technically, the equation is X plus 4 if X is greater than or equal to 1. So instead of it being the whole graph, and so that's what the whole graph looks like. What you would do is say, nope, go to X equals 1 and erase everything before that. So B of A of X is actually only the graph of the ray.